So, hello, welcome. I am Terrell Russell. I work for the Irods Consortium. We have our own booth around the corner. I don't remember the number, 3628. Write that down, it's very important. I'm going to talk a little bit about today about Irods and reproducible science. But reproducible science, you could also consider reproducible business practice, reproducible policy, anything that you want to really consider doing over and over again and being able to prove it later. So I work for the Irods Consortium, which is an organization, a sub-organization under RINC. RINC is a research institute at the University of North Carolina in Chapel Hill in North Carolina. All of our stuff is open source. I'm going to talk about two problems today, and then I'm going to give you the solution. As it should be, the answer will be Irods. I'm ruining the surprise. So problem one, we have a lot of data. It's coming in very fast, and every year, 90% of the world's data is created again. That's probably been true for a while, for the last few decades, which kind of bends your mind a little bit. It's coming in too fast. We don't really have good source information for where this data is coming from a lot of the times. If it comes from different people, different sources, somebody's probably not necessarily writing that down as well as it should be. People store it wherever they have room that day. That could be on a drive, that could be on a tape, it could be on a drive from 5-10 years ago. Things get lost, things get corrupted, and certainly things get forgotten. This is a problem that everybody has. Problem two, turns out science is hard for a variety of reasons. It's built on theory, it's built on hypothesis. You've got to have all of this. You've got to have experimentation, you've got to have measurement. There's a whole branch of science around measurement. And then you've got to iterate. All of these things are hard. But above all, it must be falsifiable. It's not actually science unless you have something that you can actually test and prove that it's true or not true. It also must be repeatable. So repeatable science is what makes it science. But not only that, it's got to be reproducible by other people, right? Just because you say you did it again, that doesn't necessarily count. You write a paper, somebody else writes a paper, somebody else writes a paper. If they do it the same way, now you have some science. Congratulations. So scientists, and of course the people that work with them and around them, and the people who give them their networks, they know where the relevant data is, and they have to know how it's handled over time, and they have to have a plan for keeping that data around in a good way, or else, again, the science doesn't count. Right? All of this knowledge that we've gained, the things that we've trusted, the experimentation we've done doesn't matter if you can't prove it again later. And that's pretty hard already. But it's coming down the pipe now that publicly funded science, things where you get money from a government, you're starting to get a mandate alongside the publication of your process and the publication of your science. You're now having to have a plan for both the data management as well as the storage for at least 10 years. This is not a surprise anymore, and this is, I think NIH now has a 2020 plan where you have to have things around for 10, 15, 20 years. Not only that, it's not only for 10 years, it's actually 10 years from the last date of access of any particular object in your system. That, of course, means that you have to keep track of all of that, never mind the actual process of handling all that for 10 years. What that includes is verifiability of the data. That data has to be migrated across different pieces of hardware, different technology stacks. You've got to keep it in duplicate, because what if one of them gets corrupted? What if one of them falls over? You've now missed your mandate if you don't have more than one copy. It has to be accessible, because part of this data mandate is that it be publishable, shareable, discoverable by others. Again, if you're not doing that, you're not actually doing science. And of course, all that has to be monitored in case something does go sideways so that you can fix it. And that's hard to do by hand, so you really have to do it automatically or you're not really doing it. So here's a bunch of words. All of these tasks are hard enough, right? You've got people who are paid information professionals, librarians. They can't do this by hand. The scientists aren't going to do it by hand. There has to be a policy at the organization layer to be able to deal with these problems and keep this stuff around for that mandated 10+ years. You've got scenarios around retention, you've got scenarios around access and data use. There must be automation in place or it doesn't count, it won't happen. You will lose things and you will be in violation of whatever mandate that you probably are under. You have to have confidence in your process, you have to have confidence in the stack that you're using, and generally that's going to be an open process if you want to be able to trust it and hand it off to somebody else, or be able to find talent to run it for you. If they already know the thing, it's much easier to find them. And so here's a slide about, from Unilever actually. They gave this presentation at the Mass Storage conference earlier this year and said most big science is no longer a single scientist in the basement working hard for 10, 15 years and producing science, right? That's not how it works anymore. Generally now everything is multi-institute, big money, multi-author, and moving at great speed, right? Things are now modeled, things are now computationally intense, things are now distributed. This is much harder to keep track of, and if you're not writing all of those steps down, you don't have science, right? It's the same problem, but now accelerating. So these complexities around storage and collaborative work, this is only going to get worse. You need to have a plan, right? So this is the legitimizing part. Ta-da, here's the answer. We think we have the best solution available. It's open source. It's called Irods. Irods does 4 things. It provides data virtualization. It provides data discovery. It provides a rule engine whereby you can actually automate this policy, where you're keeping track of where everything is. You can actually take action based on metadata, based on who's doing something, based on access times, based on the weather, based on whatever you want it to be based on. You can take action on your information and move it around, keep track of it, including all of the provenance information of where it came from, how many times it's been transformed, and how many times it's been moved. Because it's open source, Irods allows you to federate with other instances of Irods. That other instance can be at another institution. It can be at another department in your institution. But the point is, once you have this policy in place, and once you're actually doing real science and keeping track of everything the right way, you can now work with others who are doing that independently with their own policy. They may not have a mandate the same way that you do. You may have health information data. They may have stuff that they don't have to necessarily anonymize as much. With federation, if you go across that bridge and log into another system, their policies are in force when you touch anything in that system. If they visit you through the right access controls, your policies are in place. Your stuff is in force when they come and touch anything in your system. This is very important. You authenticate at home, but any policy that you trigger will fire where you do the work. So I've got 2 scenarios, 2 design patterns that Irods as a consortium have identified in the public. So one is data to compute, the other is compute to data. So the first here is where you've got massive amounts of instrumentation bringing data in off the left side. This could be automated, this could be in volume. We've identified this as a pattern by calling it a landing zone. So the idea is that inside of this dotted line, this green dotted line, Irods is aware of that. And Irods can watch a folder, watch a collection, watch a directory where new stuff is coming in all the time. It might be a very fancy file format. It might be coming off of a satellite or out of a microscope or something like that. Irods can fire policies when it sees something appear, extract the metadata, put the file in the right place, whatever that's defined to be by your policy and your organization, pull the metadata out, make it searchable, make it discoverable, as well as stage it, do checksums, make 2 or 3 copies, email the boss, whatever it's supposed to happen when data like that shows up. The hard part here was always moving from that long-term storage over to HPC and back again when some scientists wanted to do some work. This can now be done by metadata. When someone gets ready to do some science on the expensive hardware, they can simply tag the things that they need to tag, bundle them together, provide some metadata, and then again, a policy could awake every hour, every 2 hours, whatever, do a search across the entire system and look for jobs that are ready to be run. It can then stage the appropriate data to the fast disk, jobs can be fired, and then the results can be automatically ingested back into the namespace, and then the copies that were on the expensive disk can be trimmed automatically. So you're maximizing the usage of the expensive, fast, parallel file system while and getting the people out of the way. You're no longer waiting on the lab assistants to move data around for you. This is one use case. The other use case we've noticed is the opposite, where you want to take the compute to the data. If you've already got particular hardware stacks and particular software stacks in your environment, maybe you've got all of your water science stuff over here and all of your space science stuff over here, and this one does things with image analysis. You don't want to move that data around again. The data is already resident in the right place because you've done something in smart and used your policy and gotten it distributed. Now when a compute request comes in from a user, that compute request can actually be routed to the right place and run on the right hardware. And so you can use these two scenarios to envision a little bit of one, a little bit of the other can help you solve whatever use case you've got in your organization. And so writing these policies is an exercise for you. We're here to help you if that's necessary, but the idea is that you get the toolbox and you can build what you need. So I'm going to go quickly through 4 use cases, and then I'll be done. I'm going to talk about these because they show orthogonal use cases for the different ways you can do metadata and why they actually help. So the Wellcome Trust Sanger Institute is a publicly funded institute with a mandate in the UK, and they use Irods to do single sign-on, handle their durability, HPC, and their metadata scenarios. So their typical data flow, they have some sequencers. Data comes in. They do a lot of quality control and alignment. That's outside of Irods. They've got a lot of scripts and people and science and wet labs, and they do all that kind of stuff before it gets into Irods. They then ingest the data. They stage it to Luster. That's the HPC side of their work. The science drops out the bottom. It gets re-registered back into Irods. And then they use Irods both for their archival storage as well as for their publication, because they too have a publication mandate, being a public institute. They use that to power what the data that's served by their web server. They also use Irods in a federation manner within the same institute. So they actually have a portal zone where everybody logs in. The entire institute is Kerberized. So they go through Kerberos, and then from there they bounce across the Federation bridge to whatever data sets or sections of the company that they need, of the institute where they need to get the data. So there are different policies in force for the human genetics data set than there are for the sequencers, than there are for the archive. There's different policies in place to make sure that things are kept in the way that they need to be kept. Some of these are on faster disks. Some of these are in triplicate rather than in duplicate. Some of them are checksum differently. The whole point is that they are handled and managed by different people with different policy goals and different organizational control. The second of the 4 use cases is about the NIEHS. So NIEHS is also in North Carolina. They use Irods. They use metadata to drive their workflows, and they actually do it for their reporting and billing. It's not as much about the largeness of the data as much as it is about pipelining a human sequence of events and making sure that it became much more regularized, and they can actually assume, based on the patterns and the policies that are being enforced, what happened inside the institute, so they know who to bill. And when they write their quarterly reports, it's basically just a query into the engine rather than people running around and having meetings and writing a bunch of spreadsheets. So they actually they create designer viruses based on particular requests, right? They're doing science for the government. That's what happens sometimes. So they do all of their work in the wet labs, but they also need to go through quality control, sample delivery, and write reports, same as what Sanger was doing. But they had a problem where the spreadsheets were irregular, and the people creating these things were not using the schemas in a way. They weren't being enforced. And so you had slightly messy data coming through the... When you add people, that's what happens. You get slightly messy data. So they are actually able now to produce things at the end and to the penny assess what their costs were, who to charge for that, as well as being able to predict trends. Because now they have historical data going back as long as they've been running this. They can see where the dips and the flows are every year. They can tell what seasonality they've got in their usage. The third one is actually NASA. They're going to use metadata around their migration patterns, around publication and federation. So NASA's been doing NASA things for a long time. They've had a lot of data on a lot of different storage technologies. Irods allows them to virtualize that and migrate cleanly between physical storage technologies and provide a common namespace across all those different things. So they had a bunch of different storage technologies. They had a system called Angie, which was their metadata engine, They're still using it, but now they use Irods in a complementary manner. So they're storing some information in Angie, but now they're doing a lot more in Irods. They had a DPO, which was their elegantly named Data Products Online. It's a good name. That was their publication engine. So Irods is now sitting atop the DPO and providing it with the storage backend. So DPO is now Irods aware. So that was very interesting. They were using metadata now to manage the migration, to manage the publication, as well as to manage some of the federation, because the Goddard Space Flight Center, independent of the Atmospheric Science Data Center, started using Irods at about the same time. And it turns out that they each had data sets that are fairly unique. The stuff that NASA makes is expensive to make because it happens in space. Nobody else is up there. So independent, their data set was very valuable. Independently, their data set was very valuable. And now they could actually federate and start to use each other's data without having to copy it around, move it, as well as the fact that they could now log and audit what was being shared, and again, use that for their own reporting and making trend assessments going into the future. The last example is the University College of London. They use metadata to actually manage their tiering and their retention policies. So the UCL actually is a big DDN customer. And so UCL is using their repository magic to keep track of research data across a bunch of different domain sciences: social science, physics, genomics. And of course, they have this public mandate to keep stuff around and accessible from 10 years from the last date of access, which means they have to track date of last access for every single file in their entire system. That's impossible for a person to do. Luckily, we have computers. Congratulations, they figured it out. So Irods now spans that storage technology, both in time as well as the technology itself. So they use the GPFS for their fast stuff. They also have scalable object store, which in this case is a WAS. And then they have a lot of tape. And they can go and get from that tape based on date of last access. They can tier automatically based on Irod's rules and policies, keep things in the right place. If it's relatively warm, they'll have it in the object store. If it's relatively cold, it'll be in the tape. And if it needs something to do something fast, it needs to go to the parallel file system. And that can be automatically managed once they write the policy. The hard part is deciding what the policy is. The relatively easy part is writing that policy down in the rules. And the really easy part is not having to worry about it anymore. So policy-based data management is the story. It's because we have too much, because this stuff is hard. You have to do it with a policy engine. You can't just have an arrangement and have people expected to be, they retire, they graduate, they go to a different company. This way it's in code. And then of course that data management must be automated or it doesn't really count. That's all I have unless you have any questions. Who has the disk? So Irods is open source. We are not a service. This is yours. You run everything. So that means that you are running the drives, you're running the tape, you're running the servers. This is all on-premise if you want it to be. Irods is open source software. You can download it and run it wherever. We know of a lot of installations around the world, but we assume there are many others that we don't know about. So I think you're asking, why would we be around tomorrow? Thanks for the plug. So the Irods Consortium is, so Irods is about 20 years old. The first 10 years was NSF and DoD funded. How do you do grid storage? This is hard. Here's a bunch of money. 10 years is up. We figured it out. Not hard anymore, right? The next 10 years, because it's hard, how do we apply a policy engine on top of that? Nobody done it before. We figured it out. No more money. So now the idea is it has to be sustainable, right? They're not going to give you money once it works. That's not how it works, right? So we are now a consortium. So once people use Irods and it powers their system, members join the consortium, pay an annual fee because they care, and then they get a voice at the table. They can vote on the things that matter to them. They can vote on the bugs. They can vote on the features. They can vote on the roadmap, as well as have a voice in the actual governance of the consortium. And so because we're at a university, nobody can come and buy us. right? We're not. We have our membership is largely defined by storage vendors and like DDN and institutes, governments, people running large data systems, and so they join, and then it works. Anything else? Thank you.